What's up guys, James here with Fun Fact of the Day. Hope you guys are having the best day you've ever had in your entire lives, learning lots and getting stuff done. Today, we are here to talk about neutron stars. You see, yesterday, the world's largest neutron star that's ever been discovered was discovered and measured, and it was huge. I was wondering, what is a neutron star? My whole family also was wondering the same thing, so I figured all of you were too. So that's what we're going to talk about today. What is a neutron star? In order to really understand what a neutron star is, we're going to first talk about how it's created. Now, you've probably heard of a star. The sun, in fact, is one of these. And over time, they just get huge. They get bigger and bigger and bigger, and eventually they get too big and they start to collapse in on themselves. They get too heavy. Basically, they get fat. Eventually, all in 1 second, it will hit a tipping point where it starts to implode. And this is where the process of what you might have heard of as a supernova is occurring. Inside of a star, there is a material called silica. And when that star gets big enough that it reaches that tipping point, it starts to turn into an iron variant. You've heard of iron. It makes fences and swords and things. Anyway, once this happens, the entire process starts. The gravity grows tremendously as this iron is formed, instantaneously. And then the entire thing, because of all the extra gravity, is sucked in together. Now, we're going to take it to a molecular level. Now, you've probably heard of an electron. They're the little tiny things that orbit around the nucleus of an atom. These things don't like to be pushed together. They hate it. They're like two magnets when you try and push them together, and they don't want to touch. That's what electrons do. This is called electron degeneracy. But because there's so much pressure sucking this thing together because of all the gravity, it actually pushes all the electrons together anyway. That electron degeneracy fails, and the entire thing squishes together. So those electrons and the protons and neutrons that are in the nucleus of each atom get squished together to form a whole bunch of neutrons, which are basically tiny neutral particles inside of an atom. Now, because the star was so big and this collapse is so impressive, it keeps going until the ball of neutrons is the size of a small city. Think San Francisco, but in ball form. But it used to be bigger than the sun. So, you can imagine, it's a pretty heavy, dense little ball. And then those neutrons, they don't like to be pushed together too much either. Think of two golf balls getting pushed together. They're pretty hard. They don't like to be squished, but it happens anyway. So, all of those neutrons actually collapse in on each other also, just like the electrons did, to the point where they eventually just hit a wall. And at that point, everything starts to go backwards. There's too much pressure, and it kind of rebounds. And that is where the supernova occurs. The star explodes from that rebound. It is amazing, and I'll play a video right here of a supernova so that you can understand what I'm talking about. After all the metaphorical smoke clears, what's left over is the most tightly packed ball of neutrons you've never even thought about. And this little ball is the neutron star that we were talking about. It is the most dense thing there is, pretty much. There is one more dense thing, black holes. But we're not talking about that today. We're talking about neutron stars. Just to get an idea of how dense this little ball is, imagine your average atom, the things that make up us, as your old high school gym auditorium. The nucleus in that, the center, is probably about the size of a really, really tiny grain of sand in relation to that gymnasium. And then, all the electrons that we were talking about earlier that got squished, those are the little bits of dust around the very edges of the auditorium that your janitor never actually cleans. So, when it gets squished together, all the other auditorium atoms get squished to the point where those dusts and sand particles are all touching. To get an idea of how dense we're actually talking here, I want you to imagine every single human being in the world, okay? Now, you want to squish every one of them together until they are the size of a marble. That is about the density that we're talking about here. It is insane. if we were going to take it to a larger scale, the actual scale, the star discovered today is about 30 kilometers wide. That's about 15 miles, roughly. That is about the size of a large city in diameter. So imagine a ball about the size of Chicago, but it has 300,000 of our sun packed into it. That is how dense this neutron star is. Now, these things, because they're so dense, have quite a bit of gravity. They have a giant gravitational pull that surrounds them. So, if you were to take Google Maps and drive your way on over to this neutron star out in the middle of nowhere, the gravity there is about 100 billion times stronger than our gravity. So, on there, I, weighing 225 pounds, would actually weigh 22.5 trillion pounds, which is quite a hefty guy. I'd definitely have to cut back on some carbs. But I would also be less than an atom thick, because it would squish me completely flat. That's how much gravity these things have. It's really amazing. Now, let's talk about the exact one that was found yesterday. It is called a pulsar, and it's called that for a reason. Basically, this neutron star, when the supernova happened, it shrunk the entire thing. Obviously, it was the size of a giant star. Now it's a tiny ball. And when that happens, the speed that it was spinning increases. Imagine back in the day when you were on a tire swing, all right? And you were swinging around, spinning in circles, and your legs were straight out. But when you sucked them in, you start spinning way, way faster. Or maybe an ice skater, when they start to suck in, their twists are extremely fast. The same thing happens to this star, but to a much greater degree. So these things can be spinning around in circles hundreds of times per second. And because they have so much gravity and so much magnetic force coming out of them, they actually shoot off a whole bunch of radio waves, X-rays, and beams of light from the poles of the neutron star. So, it's basically like a lighthouse. Imagine a light slowly turning in circles. It's kind of pulsing, hence the name pulsar. Now, this light and radio waves and X-rays, they shoot for miles and miles and miles, thousands of light years, because they're just so powerful. And we actually have the technology to pick those things up. Now, because there are so many things like this coming in, it's tough for us to differentiate where these things are out in space. But fortunately for us, a small moon planet thing passed in front of this star, and that disrupted the pulsing waves. So we were able to determine, because of that, how big it was, how far away it was, and just how fast it was spinning. This pulsing is actually so consistent that about 40 years ago, we thought that aliens were seriously responsible for it because it was just so perfectly timed. Now, before you go, there are actually a different type of these neutron stars. They are called magnetars. I know, it sounds like a Pokemon. Basically what these are pulsars on steroids. They are insanely powerful. They're like super duper duper dense magnetized pulsars. Now, because there are no words in the world to describe how much more impressive these are than a normal one, I'm gonna have to drop some numbers on you. So take a seat. Let's start with the anatomy of this thing. So, these pulsars and magnetars, their basic anatomy is that they have a very, very thin kind of crystalline crust, and then they have the inside. And that crust is magnetically connected to the rest of the inside. But if it shifts even a couple millimeters, it can cause basically an earthquake, but a magnetic version of it. Now, in the sun, when this happens and it has a little magnetic outbreak, we get what's called a solar flare, which is nothing to scoff at. It's usually billions and billions of nuclear bombs equivalent, and we can actually feel them from here sometimes. But this thing is a little bit different than that. One tiny blip of magnetic pulse from this crust moving a millimeter can put off about as much energy as the entire sun does every 250,000 years. Yeah, that's 250,000 years of sun energy in a second. So it's basically a super solar flare. It's about 1 trillion times stronger than a normal sun solar flare. Now you're probably thinking, what's the big deal? Who cares? Well, one of these actually happened in our lifetimes in 2004. And, fortunately, we actually had satellites up there that were made to detect these types of things. And it actually made them all go blind because the X-rays that it sent out were so strong that it overloaded all of their computer systems. Now you're probably thinking, big deal. They blinded some satellites. But the power is nothing to be scoffed at because that wasn't like a solar flare where it's right down the road. This was 250 quadrillion miles away from those satellites. Yeah, try and let that marinate. Fortunately, this has only happened once in the last 40 years, so it obviously doesn't happen very often, and that is pretty much everything you'd ever need to know about magnetars, pulsars, and just generically neutron stars in general. So if you want to go back and reread whatever article you read yesterday about the giant, big neutron that was found, it'll probably make a lot more sense. If you enjoyed this video and you'd like to see more that are usually a little bit more lighthearted and easier to digest, please click the link right here. I have a whole playlist of them set up just for your enjoyment. Thank you very much. Like, subscribe, it really helps out the channel, and I will see you tomorrow.